Let's discuss proof methods and strategies in discrete mathematics today. Sometimes proof can be established by examining a relatively small number of simple cases. It's not necessarily true that if a core principle holds in one scenario, it holds universally. We only need to verify the inductive step in the inequality. For instance, when n equals 1, 2, 3, and 4, we assert that 3 raised to the third power equals 27, 3 raised to the fourth power equals 81, 3 raised to the fifth power equals 243, then 3 raised to the sixth power equals 729. It's straightforward for us to use these few numbers to prove that the list is not associative when the cube of 3 raised to n plus 1 is greater than the cube of 3 raised to n. Using proof by cases. Some mathematicians enjoy proof by cases because it covers all possible scenarios that arise in the theorem. For example, let's prove that if n is an integer and n squared is greater than n, we can establish this by considering several cases. When n equals 0, when n is greater than 1, or when n is less than minus 1. In the first case, since 0 squared equals 0, we see that n squared is greater than or equal to n. In the second case, when n is greater than 1, multiplying both sides of the inequality by positive integers, we obtain n squared is greater than or equal to n. In the third case, although n squared is greater than 0, it follows that n squared is greater than n because for any negative number, squaring it results in a positive number. The process of proving a theorem often involves a systematic approach. For instance, decision proof is a method of proving, and there are several ways to prove a variety of results. Let's consider an example. Show that the number 100,729 can be expressed as the sum of the cubes of positive integers into two different ways. After considerable calculation, we find that 100,729 equals then 10 cubes plus 9 cubes plus 3 cubes equals 12 cubes plus 1 cube plus 10 cubes. Since we have this display, a positive integer can indeed be expressed as a sum of cubes into two different ways. When proving a statement, it's crucial to demonstrate that an element with a specified property exists and that no other element has this property. The two parts of such a proof are extant. When you were sure an element X with the desired property exists, and uniqueness, where you show if X and Y both have the desired property, then X equals Y. For example, to show that if A and B are real numbers and A is not equal to 0, then there exists a unique real number R such that A times R plus B equals 0. We find that R equals negative B divided by A is a solution because a time negative B divided by A plus B equals negative B plus B equals 0. In conclusion, there is an additional proof method called proof mastery. We describe how to leverage this method to prove a variety of results, and we will use proof mastery in all subsequent chapters. Different proof methods can be used to solve different problems, as not all strategies work for every situation.